Boom! All right. So in this video, which is a continuation of our series on differentiation, we will introduce the concept of the limit by demonstrating it first on a curve that we're already familiar with, on a curve that we have been discussing extensively up to this point. And then we'll go general and make it a little nice. All right? So before we do that, let me just write down something here which is very, very important. We saw that this thing seems to approach 2, and we assuming for now that 2 is the limit, we will get to the point of proving that in a little bit. But we could say that the limit of change in y over the change in x, all right, is equal to the gradient of the tangent as we demonstrate here. Let me say the limit as the I need to write it out bigger. Don't worry, we will explain this in more detail just now. You can say the limit as the, let me say the chord length tends to 0 of change in y over change in x is equal to the gradient of tangent, right? In other words, the gradient of the tangent is the gradient of a chord whose length is 0. Right? That is what that, yeah, the gradient of a chord. Remember, the tangent is the extension of the chord, right? If the length of the chord is 0, and you extend the line, that's the secant line, that's the tangent. All right, so don't worry too much about that. We will clarify that a little more as we go along with some extra additions to the lingo. So let me consider our friend, our good friend, the curve y is equal to x squared. All right? So let me go general now. All right? Let us say we have a point x, and let me say we have a point, all right? I'll leave it just so. Right, so this is your curve, all right? So this is the general point x, and this is the general point. Watch it now, x plus delta x, where delta x is this length here. That is the change in x between these 2 points. And naturally, the y coordinate will be, this will be y, and this here would be delta y. Sorry, right? This will be, all right, let me need to get rid of this now. This here will be the point y plus delta y. All right? So let's see how nice the maths is starting to get now. This is the point 1.001, 1.002001. All right? Right. So the x coordinate, let me say this is the y-axis, and this is the x-axis. All right? This is the curve y is equal to x squared. So, in the same way that from here to here, delta x, in the same way, delta y will be here to here. That is the change in y. Right? Right. So this is your delta x here. and that's a delta y here. Right? So in other words, the gradient of this line, general line segment, would be delta y over delta x. The problem though is that y is equal to, so in other words, this here is the point x, y, and this here is the point x plus delta x, sorry, x plus delta x, comma, y plus delta y. All right? No, sorry. Right, in fact, let me make it more, but this point, sorry, remember y is equal to x squared. So if y is equal to x squared, watch it now, then this point is also the same thing as x plus delta x, comma, x plus delta x squared. That is your coordinates right there. And this point is the point x, comma, x squared. That is one point, and that is the other point here. Right? Right. So in other words, delta y is equal to x. Delta y is equal to x plus delta x. Let's see what the gradient is now. The gradient would be the change in x, change in y over the change in x, right? So the gradient, now we're going to rub off here because we need some serious space across here now. All right? Watch it carefully. All right? Get rid of all of this. The gradient, let me call it m now. The gradient m is equal to the change in y over the change in x. The change in y is what? Y plus delta y minus y, that's delta y. But we established that the x coordinate is x plus delta x squared. So it will be x plus delta x squared minus x squared. So the change in y will be x plus delta x squared minus x squared, and the change in x will just be x plus delta x minus x. It will be x plus delta x minus x. All right? So this is the x coordinate here. This is the y coordinate here. So in other words, y2 minus y1, y2, x2, y2, this is x1, y1. Right? y2 minus y1 over x2 minus x1. Don't worry, we'll go through it again. This is equal to x plus delta x squared will be x squared plus 2 delta x plus delta x in brackets squared minus x squared. It's 2x delta x. X squared plus 2x delta x all over x plus delta x minus x. So it will be x squared, no, I'll try this over x squared plus 2 x delta x plus delta x squared minus x squared. The x squares will cancel out. All over x will cancel out. All over delta x. Alright? And hold on. Something missing in the book in here. Alright, so hold on. Let me just double check this thing in the working. Yes, I have my books here, you know. Alright, no shame in the game. X plus delta x. Hold on. Hold on, no shame in the game. 2x delta x. Yeah. Oh, right, I understand it now. I now see what happened there. So the x squares will cancel out here. Just as how the x cancel out here, the x squares will cancel out here. So what we'll end up with at the bottom, now I have to squeeze it now, will be 2x delta x plus delta x squared all over delta x. Alright? Yeah, I had to double check the work in there. But I know I read it and I understand it, but when I was writing it out here, I kind of forget now. You know? We cancel, we factorize. You get delta x, you get delta x into 2x plus delta x all over delta x. Delta x will cancel into delta x, and you'll get 2x plus delta x. So this here is the gradient between any two general points on the curve y is equal to x squared. So let me run that through again. You have the curve y is equal to x squared. Alright? Pay attention, right? Because whatever I miss, you had to get it here, and if you didn't get it here, you have to rewind after that. Alright? So we have 2 points, the general point xy and the general point x plus delta x, which is the difference between two x coordinates. And if this is x and if this is x plus delta x, then this will be x squared because y is equal to x squared. Right? Y is equal to x squared. So this will be the point xy, which will be x squared. And this will be the point x plus delta x, y plus delta y. Y plus delta y is equal to x plus delta x squared. So in other words, the y coordinate will be x plus delta x squared, the square of the x coordinate, which is x plus delta x. The gradient of the line segment joining these 2 points will be delta y over delta x. Delta y over delta x. Delta y would be this y coordinate, which we already established as x plus delta x squared, minus this y coordinate, which is x squared, y2 minus y1. Boom. The x, delta x, would be x plus delta x, which is the x coordinate here, minus the x coordinate here, which is just x. We get here x plus delta x minus x. So we squared. I'm not even explaining how I get this. This is add maths. The expansion of a plus b all to b squared, that's as much as I've given it. Right? You could get this in the maths website too, on my maths website, or you could get it in a multitude of other places. But add maths is not the place for me to explain that. Right? Alright, I've thrown all into the deep end there now. A plus b in brackets all to be squared. End of discussion. Go and look for it if you need to. right? X squared plus 2x delta x. I'll write this a little more clean. X squared plus 2x delta x plus delta x ought to be squared minus x squared. X squared minus x squared will cancel. This will give us, right, so we could cancel out here now. Right? And you'll get that. So we could actually borrow some space here now, just to make it look a little more, right? So we get the x squares cancel out, and the x squares will cancel on top, and the x's will cancel below. Yeah? Right? Minus x. So here you have this, and then when you factorize, you will get delta x into 2x plus delta x all over delta x. The delta x will cancel out, and you'll get just 2x plus delta x. Right. Now is where we start to get the crux of the matter now. As delta x tends to 0, which is to say, as this point gets closer and closer to this point, both delta y and delta x would tend to 0. Right? But in the formula here, we only have delta x. So we need to change the color of the ink now. So the limit as delta x tends to 0 of 2x plus delta x would simply be 2x. And at the point where x was 1, 1, at the point 1, 1, x is equal to 1, so that limit will be 2 by 1, which is equal to 2. Right? So in other words, at every value of x, you just substitute it into this expression here, and you get whatever the limit is. So the limit at x equal 2 would be 2 by 2 is equal to 4. The limit of the gradient at x equal 3 would be 2 by 3 is equal to 6. The limit of the gradient at x equal 4 would be 2 by 4 is equal to 8. The limit of the gradient at x equal 5 will be 2 by 5 is equal to 10, etc., etc., etc. What that means is that the gradient of the tangent at x equal 1 would be 2 by 1, which is equal to 2. The gradient of the tangent at x equal 3, which will mean the point 39, will be 2 by 3, which will be equal to 6. The gradient of the tangent at the point 416, in other words, the gradient of the tangent at x equal 4, will be 2 by 4 is equal to 8. And the gradient of the tangent at the point 510, the gradient of the tangent at x equal 5 will be 2 by 5, which is equal to 10. And that, or I should say this, ladies and gentlemen, is how we get that, watch it now, the gradient, we say dy dx of x squared. Sorry. Let me make it more. That is how we get that d dx of x squared is equal to 2x, right? So in other words, we have just shown that d dx of x squared is equal to 2x. We could also write it as dy dx of x squared is equal to 2x. We can write it like that too. Right? So this fella here, take a note of it. It's not that you have to actually remember it, but I wanted to remember it as the culmination of a whole lot of calculations and talk and graphs and everything. This is what we end up with when we're talking about the curve y is equal to x squared. So the next step, is there anything else that I need to say here? The limit of, all right, I will do that in the next video. So the next step is to go beyond y is equal to x squared, because y equal to x squared is just simply one specific curve. This that we just did for y is equal to x squared could apply for any curve. Once the curve is differentiable or differentiable, I think differentiable is the proper word. Not all curves can be differentiated, but that's a different discussion. Once the curve is differentiable, once you could differentiate the curve, we can apply that same concept to any curve. We could apply that concept to the graph of y is equal to x cubed, y is equal to x to the power of 4, y is equal to 3x squared minus 6x plus 2, etc., etc., etc. Once the curve can be differentiated, right? So if we established, and it doesn't have to be a quadratic curve. It could be a quadratic curve, it could be a cubic curve. It could be a logarithmic curve, it could be an exponential curve, right? There are different classes of curve. And once a curve could be differentiated, this same concept can be applied. So what we're going to do in the next video is go even more general. Here we went general on y is equal to x squared. We'll go general on some curve where we don't even know the equation of the curve. We'll just represent it as f of x or some kind of generic thing like that. And we will drill down into a more general form of what we have here, the limit. This whole question of the limit, where we're talking about differentiation, we're talking about the gradient of a tangent, etc., etc., etc. So, stay tuned. We have more things coming up.